So my name's Tom Hall. I'm known on several internets as that Tommy Hall. That's the safe for work version of my avatar. I usually show a slide from where I'm currently employed. I'm pleased to say recently I've changed to be self-employed again, and I'm in the process of starting a co-op with some friends, which we've called the Department of Binary Affairs. So sometimes when I go to conferences and they happen to show it, people think I work for the government or whatever, which makes me laugh. I also give myself the title Minister Without Portfolio, which, if you know UK politics, is an actual position. So I did a little while ago SICP Distilled. That's grown bigger and taken longer than I originally planned, but you might know me for that. If you did back that on Kickstarter, I have some good news for you in a little while. But what I'm going to be talking about today is unlimited register machines, and I'm going to show you a concrete implementation of the universal unlimited register machine in Clojure. So I originally came across this idea in a book by Nigel Cutland, An Introduction to Recursive Function Theory. So this is, your unlimited register machines are a formalism a bit like Turing Machines, or perhaps the Lambda Calculus for describing computations. They're simpler. The formalism, or the version of an unlimited register machine that Cutland uses, is different than the one I'll be talking about today. And I'd studied this a little while ago, but very recently I read a book by my favorite contemporary philosopher called Dan Dennett, and he has a whole section about understanding the machine, so understanding this idea of universality and trying to get everybody, including laymen, to have an appreciation of what it is that computers do and sort of remove the mysticism from them or whatever. So I meant to say there's sort of several levels at which you can come away from this talk. Level -1 is meh, I suppose. Level 0 is, oh, there's 3 or 4 books I might read. Level 1 is, oh, I think I understand unlimited register machines. Level 2 is, oh, I think I've sort of glimpsed at the universality. Level 3 or whatever is probably that you understand the universal unlimited register machine. I should warn you that there's a lot of stuff kind of compressed, so it's probably like half of an undergrad course compressed into 30 minutes. So it's supposed to be a sort of whistle-stop tour or to sort of whet your excitement or whatever. So don't worry if you don't follow everything, but I hope it's enough to kind of perk your interest. So the particular URM that Dennett introduces, I had a look at where other courses were using unlimited register machines, and I found one course at Cambridge that had a good treatment of it. So some of the functions and subroutines and stuff I use are actually taken from these notes from Andrew Pitts at Cambridge. So I should probably say what a universal machine is. So an unlimited register machine is, so a register is a place to hold natural numbers. So there's no limit to how big they can be. And it's unlimited in a few other ways. So you can use as many registers as you like, and they can hold a number of any size, but there's only finitely many registers in every program. So a program is a sequence of instructions, and again, this is finite. You are allowed to loop, so your programs can run infinitely long, but they can't be infinitely long. And the 3 instructions in the URM we're going to look at today is end, which means you're done. Increment, which means to increase the number in the register by 1. And then every instruction, except for end, except for the halting instruction, is a goto. So increment register n, and then go to line m in your program. And then you may know from other things you've seen in terms of being Turing complete, you need some way of branching. If you can't branch and you can't loop, you're not going to be able to express all possible computations. So the only branch you have in this is the instruction called deb, and deb stands for decrement and branch. And what you're saying here is decrement register n, and if you can successfully decrement it, go to register m. So what does it mean, successfully decrement? Well, we're holding integers, and we're not allowing negative numbers. So if you try and decrement register n, and it's already 0, instead of going to the first instruction, m, you'll go to the second instruction, p. Is that clear? Oh, I should say, I have a regional accent, and I'm from the UK, so I think like when you're swimming, if you stop understanding me, I get too excited. Wave your hands like this, and I'll try and slow down, and I'll try and be more comprehensible. Can everybody understand me so far, though? I guess I need a positive signal here. Cool. So as you're computing, you carry around a state. So there's a program counter, which is basically an integer just saying what line in the program you're on. That again goes from 0 to the number of lines in your program. You've got finitely many registers, the state of which you need to track. And you've got the program that you're executing, which again is a sequence of instructions. So computation is a sequence of states, because every time you execute an instruction, you update the state. Usually you're incrementing or decrementing a register, yeah? Sometimes you don't do anything, because if you try and decrement something that's already 0, you're just jumping around the program. So usually, except in a branching condition, every step just updates one of the registers. And you halt when you execute the end instruction. So when you say end, you're done. Or, and this is to allow us to express programs that are not valid and still have a way of executing them. So if you jump to an instruction that doesn't exist, that counts as an end condition as well. So our first program is got 5 lines, and we're going to decrement register 1 and jump to line 1. Otherwise, we'll jump to line 2. Then increment register 0, and then jump to 0. So we've got a loop there, haven't we, that says we're going to decrement register 1, and then jump to line 1. We're going to increment register 0, jump to line 0. So we're going around there until register 1 is 0. Does that make sense? Then we break out of our loop and move to line 2, and I'm going to keep decrementing register 2 and jump into 3, incrementing register 0 and jump into 2. And then we're going between 3 and 2 until register 2 is also 0, and then we jump to line 4 and we end. So does anybody know what computation that's performing? Addition, yeah, it's addition of register 1 and register 2. We copy register 1 into register 0, then we move on to the next sort of subroutine, copy register 2 into register 0, and then we return. And this is a pattern that we adopt in our formalism that says registers 1 through n, so all of these machines of variadic, we could have had whatever we wanted set as the contents of register 1 and register 2, and the sum of them will be placed into register 0. So we assume that register 0 is initialized to 0, and that our program is going to put its answer in register 0, and the inputs to the program are all the other registers at the start of the program. Does that make sense? So we can add 2 numbers together using our formalism. And a way to do it, if you're not, so I spoke through that and we reasoned about it, but we can do it mechanically. So one of the points of these formalisms for expressing computation is that you can express, or you can have a machine mindlessly execute them. So one thing to do is keep a track of which line you are, keep a track of which registers are in use. We can see from examining the programming what registers are in use, because we only decrement register 1, we increment register 0, we decrement register 2, and we increment register 0. So we know that our program only references registers 0, 1, and 2, right? So we can say, what line number are we on? By convention, we always start at 0. By convention, again, register 0 is initialized to 0. Register 1 and 2 are the inputs to our function, so we're going to add 1 and 2 in this case. And then, so what does line 0 say? It says decrement register 1, and then go to line 1. So decrement register 1, you write it down, 1 goes to 0, you're now on line 1, and then you just copy the remaining lines. Does that make sense? It's easier with a whiteboard to explain this, but now we're on line 2, we're going to increment register 0 and then jump to line 0. So the line we're on is now 0, we've incremented register 0, and we've copied the remaining 2. Does that make sense? So we can step through these things, and the idea is, and I think it just about goes off the screen before doing it, but when we're at line 2, and we're going to execute decrement register 2, and then if it's already 0, which it is, go to 4. That's our halt condition, so it's actually the jump to the end instruction is the only thing that's off screen there. So does everyone, that make sense? Mindlessly step through this stuff. And one neater way of representing it is this graphical representation. So here's a slightly trickier one. I can walk away, can't I? Yeah. I'm not relying on that microphone. So here we say decrement register 1, and then think about where the loops are in this. In this graphical notation, double arrow is the 0 condition. So if register 1 was already 0, we would end, and we would have 0 in register 0. So we would be returning 0 if register 1 was 0. Otherwise, we're decrementing register 1. So we're going here. Register 1's, we know it's not 0. Here, we're going to say, now we're in this loop, and for everything in register 2, we're saying increment register 1, increment this other register, register 3, and keep doing that until register 2 is empty. So what we've got now is 2 copies of register 2, one in register 0, one in register 3. But then when register 2 is empty, we come down here, and what are we doing here? I added that deliberately for comedic effect. When you come down here, what we're doing is we're putting register 3 back in register 2. So can anyone figure out what we're doing here? This is fairly tricky. So for everything we've got in register 1, we take register 2, we put 1 copy of it in register 0, put 1 copy in register 3, then we copy it back, then we go back and do it again. So what are we doing there? Multiplication is correct. Yeah. If you don't get it straight away, don't worry. The plan is, and I'm writing a book that's going to be on Lean Pub that gives lots of examples and exercises and stuff. And the best way to understand these really is not to have some weird fella go like this in front of you for 5 minutes, but rather to experience them yourselves and get used to designing and interpreting the URMs yourself. So if my exposition wasn't perfect then, hopefully you're intrigued enough to stare at a home and or pick up some other resources. So I'll go very briefly. This is the graphical representation from the Cambridge notes. Dan Dennett is a little, I think the notation's a little less nice. I won't go through this in detail, but this is division, and it's check division. In Dennett's notation, -3 means to decrement or branch register 3, +2 means to increment register 2. So he's more careful in one sense of registers 3, 4, and 5 are auxiliary registers. He makes sure they're zeroed out. Interestingly, he checks the divisor. If the register 2 is the dividend, or whatever the correct mathematical term is. It checks it. If it's 0, then it halts and it sets some error flag. So that register 5 in this example, all I want to say is register 5 is just flagging that there was an error. So the resulting computation is, well, as long as you don't have something in register 5, some other register has the answer in. So numbers can stand for things other than numbers. So that's one of the sort of what Dennett calls the 7 secrets of computation. So I'm about halfway, and I've said about half of the slides. So I won't spend too long talking about building the Clojure DSL, but I did the sort of wishful thinking type idea and said, well, I'd like to be able to say, evaluate a URM that looks like this, with these inputs and give me the result. I'd like to be able to turn URMs into functions. So here's our add function from before. And I say, well, if I could turn it into a function, I'd like to be able to call it like this. So that's kind of the DSL I've created. The state, as I said before, is a position. Where are we up to? It's a map of registers, which is their indexed and their value. So it's just a Clojure map. And the program is just a vector, because it's an ordered collection of instructions, isn't it, that we're going to jump around. So where are we? What's the state of our registers? And what program are we executing? That's our state at any point. So in order to run a URM program, we pick out the next statement, we apply it, and then we update the state constantly. So I won't spend too long on that. We get the next state by taking the previous state, looking up what instruction we're going to operate, applying that instruction, updating the state, and we keep running. And the run is keeps fetching the next state until two come that are identical, because the end state is the only thing that doesn't update the state. And because I've made end actually just return the state, do you see? So everything else updates the state, increment or decrement and branch, whereas end doesn't update the state. So we just keep fetching the next state until two come the same, and then we stop. So that doesn't, the particular, I know I'm at a Clojure conference, but the particular details of the Clojure don't actually matter in this case. So now we've got the sort of, if you understood that, then very good. If you're intrigued by that, then I'm glad. If you're meh, then I'm sorry. But now we're going to try and build up this idea of universality. So one thing you probably know already is that there's this idea of like a Turing machine, and it can simulate the behavior of any other Turing machine. So we're going to go for a concrete implementation. And one of the purposes of the Lean Pub book I'm going to do is to take the shortest path towards a concrete implementation of a universal machine, and you're going to see it in a moment. So these are 3 of Dennett's 7 secrets. So since a number can stand for anything, it can stand for an instruction or an address. The example I gave you briefly there was using a register to signal an error condition. If you think about all the other functions we might implement, you could have a sign register that represented whether the number was positive or negative, and you could actually treat negative numbers even though all of the registers were in the positive numbers, for instance. Or you could encode anything you've done before, like matrices or whatever, anything that can be encoded as a number, or even if you think anything that can be encoded as binary can be registered, can be interpreted as a number. You can do whatever you want. So all programs can be given a number. This is the key idea of Gödel. So all programs can be given a number. So you could if you can represent a program as a number and feed it into a machine that then takes the equivalent program and executes it, and then if you can take the input registers and encode them as a number, then your universal machine can take 2 inputs. What's the program? And what is the input state of the registers I'm going to operate on? So with just 2 inputs, 2 numbers, you could build a machine. Now, this is where Dennett is a bit hand-wavy, and Dennett says, oh, well, one could, and then that's like a sort of partial aha moment. It's like, yeah, one could, but it begs the question, well, how? So again, trying to get a concrete implementation of this idea, and this idea as well that your computers, as fast as they are just doing something similar to this, and everything is just a speed up. This is computationally as powerful as your computer is. So I'm going to talk about Gödelization, which is taking or representing something that isn't necessarily a number as a number. So for our use case, it would be great. We have to represent programs, and we have to represent the input registers. So it would be great if we could represent statements as numbers, programs as sequences of statements, so sequences of numbers. So it would be great if we could represent lists of numbers. So it's probably not going to surprise you as Lisp people that if we can, in order to represent lists of numbers, our starting point is going to be pairs of numbers. So if we can do pairs, hopefully we can do lists, which we can. Say again? So, if you may know, I didn't know until I looked it up fairly recently, but if you need to express things in binary in Clojure, you can say the base, R, and then the number in that base. So in base 2, we can write 1, 1, which of course is the binary 3. So I might have just revealed something too early then. If you're going to take pairs of numbers and try to encode them as a single number, there's a couple of ways you could do it. You could take their binary representation, you could put them end to end. If they were always the same size, you could know where to kind of split it. But there's a problem with arbitrary integers about knowing what the boundary is. You could put some known sequence in there to distinguish what was X and what was Y or whatever, but then the known sequence would obviously occur in some bunch of numbers or whatever. So the thing we adopt, and you're not forced to adopt this particular one, but the pattern we adopt is we say, well, we'll have as many zeros on the right as there is in the X number, and then we'll do 1. So that's deterministic. We can count the number of zeros, and then there's always a 1. And then after that is the binary encoding of the Y value. So we can take pairs and get single numbers. We can take single numbers and uniquely get pairs. So we've got in mathematics a bijection. We can take any two numbers, get a number, any number, get two numbers, and we're actually complete. It's a bijection. Any pair gets a number, any number gets a pair. Is that clear? No? Oh, good. I'm glad you said. It's good. Okay. I'm trying to, maybe I'll go and do one more concretely. So I have a thing for demoing. So code pair. Yeah, the pair, let's say 3, 4 is 72. So that's a number. Decode pair, and I'll show you the closure in a second. 72, 3, 4. So my function's round trip anyway. Well, there's some evidence that my function's round trip. Math jokes. So I'm saying that I can say base 2, which way around did I say? Yeah, the x value is the y value of the first thing. So 3 is 1, 0. Then there's a 1. Then there's as many zeros as there is for the other thing. 1, 2, 3, 4. Oh, sorry, yeah. Thank you. Oh, what am I doing? I did R2 rather than 2R, didn't I? Oh, shit. What have I done? 1, 1. Thank you. So besides me being 2R11. Let's code pair. This is probably why it didn't make sense to you, isn't it? 2, 3. 28. 2R. 1, 1, 1. Oh, I've got a. Ah, that's it. So I've done it the wrong way around, have I? Or no, it is actually back to front. Sorry, I've said it the wrong way around. So code pair 2, 3, and then 2R, and then it should be 2 at the end, and then the binary encoding of 3, which is 1, 1. Yeah, sorry. It's the opposite way round. The y is encoded at the front, and it's the number of zeros as there is in the x. And that is the correct example, isn't it? I had a brain fart in between somehow. I hope I haven't passed that on to you. I'm going to press on and apologize. Is that clear now? I'm glad you said no. Cool. So I could have done it the other way around, which would have made more sense. But when you come to the actual URM implementation of this function, it's easier this way around. So excuse me. There are as many zeros as x. So again, code pair 2, 5. So for this one, 2 are, and then 5 is 4, 1, yeah? And then 1, and then... why am I doing this? It's the encoding of y, so it's 1, 1, 0, yeah? One, 0, 1 is 5, sorry. And then, no, I'm not encoding 5. I'm encoding 2 first, aren't I? So 1, 0, then 1, then 5 zeros. No, fuck. This is what I mean to do, isn't it? So the other example, 160. So R2. The curse of demos. So 2 is 1, 0, as we all know. 1, and then 5 zeros, 1, 2, 3, 4, 5. Yes, okay. This is just to make it more memorable for you. In fact, here's my bloody mnemonic. Here's my mnemonic anyway. So 2RY is Y in binary. I should have, this is why I was the demo after this. Okay, so we'll move swiftly on. I've got 5 minutes left. You're laughing, which makes me feel that you're either enjoying yourselves or I'm an idiot. I'm happy with either. So what we're doing by shifting R over to the right, there's a bit shift, we're timesing it by 2 to the x, aren't we? So we can actually say, and we want to do it x plus 1 positions because there's as many zeros as there is x. Then we want a 1, then we want the binary expansion of y, so that's 2 to the power of x plus 1. That's a bit shift x plus 1 places. Then there's going to be all zeros in the first x plus 1 from the right. Then we want to flip that bit to be a 1, which is why we add in 2 to the x. That was said flawlessly, so if you didn't understand, it's your fault this time. Which when we simplify it is like this. It was flawless, I was very careful. And in Clojure, and I'm sorry, this is probably a 45-minute talk anyway, so I'm going to talk a little quicker. So we can code and decode, which you've seen it round trip. We have ample evidence to assert that the two functions do round trip. I've demoed pairs already. So if we can code pairs, we can code lists, but we need some kind of terminator, don't we? So if we can take pairs, we can say the front is this, the tail is this other thing, then we can say the front is this, and we can do console idea, but we can use actually, because our function excludes 0, so we're saying 2 to the x times 2y plus 1, that actually excludes 0, so we can keep 0 as a special number and use it as a terminator when we make lists from numbers. So I'll show you how lists are coded in 1 minute. And I might have to punt everything else off and just show you the universal machine. So if you've got pairs, you can get lists. We know that because we're list people. So if it's empty, the empty list is encoded as 0. Otherwise, we code the pair of the number that's the first thing in the list and the code of the rest of the list. Does that make sense? And it's recursively defined in such a way. And again, this is back to front. So if I say code list 1, 2, 3, the result is some number 2R. This one says 1, and then 3 zeros, 1, 2, 3, and then 1, and then 2 zeros, and then 1, and then 1 0. Okay, so we've taken lists of numbers and encoded them as single numbers. If we've got a way of coding instructions, this is going to be impossible. If we've got a way of coding instructions, but we've got free instructions and we can encode pairs of numbers. So there's a good trick that uses parity. So we're going to take end and encode that as 0, which was special anyway in our encoding of pairs, wasn't it? And we're going to say, well, whenever we encode inc, we'll double the first number. So that value for the first thing that you decode, the leftmost of your pair, will always be even. Whenever we encode deb, we'll ensure that it's odd by adding 1 to it. So I'm abusing notation here. I'm doing infix notation inside clojure notation, but I hope that's clear. And then, so whenever we decode a deb instruction, we decode it, we get a pair, and we say, well, the first thing is 2i plus 1. This first thing, we know because it's odd, we know it's a deb instruction, and we know we need to decode the second thing to get the 3 values that we need for a deb. Does that make sense? We're trying to go from numbers to instructions and from instructions to numbers. And we use an arity trick, whether it's odd or even, to use still our pairs. So is that clear? We look at after we've unpicked the number, we look at the first thing. If it's even, then we know it's an inc instruction. If it's odd, then we know it's a deb instruction. And if it's 0, we know that it's a... So we have a way of coding instructions. Again, you can check the code later. And so we can code sequences of numbers. We can code instructions. Programs are sequences of instructions, which can be represented as numbers. So programs can be represented as numbers. And So I'll just do that in Clojure, which is code the list that is the mapping code instruction across the instruction. So every instruction becomes a number. There's a sequence of numbers, which then can be coded as a list of numbers. So programs become numbers. Numbers become programs. It's not strictly a bijection, because I've cheated. You'll have to look at that in the book or talk to me. Towards a universal unlimited register machine. I'm slightly over time. I'm going to talk very quickly there, and I'm going to... Is there a short break between, or? Okay, I'll just show off the main thing in the whole piece, which is quite nice. I have, in fact, I added some extra instructions, push and pop, and copy, because they're slow in my formalism. I'm incrementing and decrementing registers step by step. If you want to take the Gödel number of a program and then copy it into another register, you straight away hit problems, because when you get the program that represents the function add that I showed you before, it's this number. So if you step by step increment and decrement that into another register, then you're waiting for the heat def of the universe or whatever for it to come out. So in order to avoid having to wait longer than I would like, he says, I can actually, I was expecting more of an aha moment, because I wanted to describe the universal machine to you, but you'll have to trust me that this is awesome. So I can code the program, add as this gigantic number. I can even add 5 plus 5, so we've gone beyond 1 plus 1. So that list is represented as that, and I can evaluate it and get 10. Do you see at the bottom there? I will have to apologize for my slightly, with a 30-minute time limit, I didn't have any room for a brain fart, and I'm afraid I had one on the coding pairs thing, but I hope it was fun anyway. That is the actual program, 15 instructions in total. It isn't self-hosting in terms of we use copy, push, and pop, but you can actually implement copy, push, and pop using the other instructions, which is quite interesting. And yeah, there's going to be a book on LeanPub. If you backtest ICP distilled, you get it for free. And any questions, probably in no time. And someone always asks me when I give talks if you can use it in your day job. Probably not. Some links. These slides are at www.thattommyhall.com/clojureD. Thank you very much for your patience and indulgence. I hope you are at least intrigued by the idea. I'm excited I will cross continents to talk about this. So if anyone wants to talk to me after, please do. Thanks very much for your indulgence.